Hi everyone. So today we will be discussing binary search. So binary search is one of the efficient ways of searching. And thing about it is that it only works on sorted arrays. So we are given this sorted nums array, which is sorted in ascending order. And also we are given a target value. We just need to return the index of our target value. And suppose if our target is not present in our array, we would simply return -1 in that case. So as you can see, the array is sorted in ascending order. So the very brute force or the naive solution of searching our target would be going traversing the entire array and going to each and every element one by one and matching with our target value. But in that case, the time complexity would be big of n because in the worst case, our target would be present at the very last index. So we would end up traversing the entire array. So in that case, we would consume big of n amount of time. But now, since our array is sorted in ascending order, we would utilize this fact. And let's see how we can solve this smartly using binary search. So let's see how we can implement binary search in this. So we would take two pointers. The first one will point to the first element and the second one will point to the last element. So let me name it left and right. You can name it anything. And every time we would compute a middle index. So mid will be nothing but average of these two values. So it would be simply left plus right by 2. And every time we would compute this mid and the element that is present at the mid index, we would compare that with our target and then take necessary decisions. So what I'm trying to say is, suppose here array size is 6. So left would be 0 and right would be initially 5. That is n minus 1. So these are our initial values of left and right pointers. So now we compute our mid. So mid is left plus right by 2. Left is 0, right is 5. 0 plus 5 by 2 is 2.5. But since this mid is an integer variable, so that's why we truncate the decimal part. So we get 2. So, and at index 2, we have 3. So now we will compare our target with this value. So we check that 3, that is our middle index value, is less than our target. This is our target and this is our nums of mid. So we see that our mid value is lesser. So what we can do is, since we want larger value, because our 3 is lesser than 9, right? So we want to search in that direction, which will gain us bigger values than 3. So since our array is already sorted, we can simply ignore this portion because 3 itself, the value present at mid itself, lesser than target. So all the values present at its left would also be lesser because our array was sorted in ascending order. So that's why we can ignore this part completely. So I hope you got the point. So since our mid value is lesser than target, we can ignore the left part completely because left will give us smaller values only. So that's why we update our left pointer and it now points to our mid plus 1. This was our mid, right? So now our left becomes mid plus 1. So this was the case. And had it been the opposite case, suppose our target was 0, let's say. Then our mid was 3, but our target was 0. Now in this case, target is lesser. So in that case, you would be eliminating the right portion because the right would give me higher values only. But I want a target which is lesser. So in that case, you would do right equal to mid minus 1 because you would ignore the right portion. And we keep on doing this thing until our left and right pointers converge. So until and unless this condition is met, we continue our process. And as soon as these two pointers converge or cross each other, we break or end our loop. And in the meanwhile, if our target was present, we would ultimately return our index there. And if not, then at the last, we would return -1. So this was the approach of binary search. Let me code it up and then it will become more clear to you. So this is the code of the binary search. So we have two parameters, our nums array and our target value. So we initialize our left and right pointers, as I told you, and we write this while loop. Every time we compute the mid value, mid index, and if our target is equal to the value present at our mid index, we simply return the mid index. Otherwise, as I told you, that if our mid value is lesser than target, then we need to ignore the left portion because left would always give me smaller values only. But I want larger target value. So that's why left equal to mid plus 1. Otherwise, ignore the right portion. So this is the code of it. And if we wouldn't have target in our array, we would simply return -1 at the end. So this was the code. Coming to the time complexity and space complexity. Space complexity is simple. We aren't using any additional space, so it's big of 1. And time complexity would be log of n. To be precise, base 2. So log base 2 n would be the time complexity of this binary search. So let me derive it also so that you would get a clearer understanding of it as well. So suppose we have this array and our target is 7, let's say. So our left would be here and right would be here. So we compute our mid. Mid is left plus right by 2. 0 plus 10 by 2 is 5. So mid will be pointing here. So now what we do, we check middle value is 5, which is lesser than target. So we can ignore the left portion because left would always have lesser values. So we can ignore that simply because we want higher value because our target is larger than mid. So that's why we can ignore this portion. So we are left out with let's 6, 7, 8, 9, 10. Now new left is here, new right is here because we did left equal to mid plus 1 as we ignored the left portion. Now again we compute the mid. Mid would be next time here. Again mid is 8 and target is 7. Now our mid value is greater than target. In this case, we want our lesser values because target is lesser than mid, right? We want lesser values. So in this case, we would ignore the right portion because right would give me larger values. So you will ignore this portion. So in this scenario, we would do right equal to mid minus 1. Now we would be left with 6 plus 7, 6 and 7. Now again, we compute the mid, we would get this. And again, we ignore this portion and finally we would get this at the end. And we would return its index, which is 7. So what one thing you would have observed that every time we are reducing our search space by half. Like here, our array size was 10 or 11 it was, and we reduced half of the portion. So it got halved. Here also you can see it was 5 elements first, but when we reduced our array search space, we got only 2 elements. So again we halved our array. So every time we keep on doing n by 2, and keep reducing our search space by half in binary search. So suppose our initial array size is n. We first do n by 2, then again half it, it becomes n by 4, again half n by 8, and this process continues until, as we remember, our while condition was left less than equal to right. So we would continue this process until left and right pointers converge. And suppose we have something like this. By converging, I mean both points to the same value. So we would continue this process until, and since both are converging means both points to same value, that means our array size has become 1 at the end. Then we would stop. So we would keep doing the half until we get 1. So if it can be written, this can be written as n by 2 to the power 0. This can be written as n by 2 to the power 1. Similarly, this can be written as n by 2 to the power 2. Like this, suppose we performed k steps. So this would be n by 2 to the power k. And as we know, n by 2 to the power k is equal to 1. So we would get this equation. Now, if we cross multiply it, we would get n equal to 2 to the power k. So k would be log of n base 2. And this is our desired time complexity of a binary search. So this is the derivation of our time complexity. So I hope this is clear. So yeah, that was it for today's video. Thank you so much for watching. And next we would be solving questions and LeetCode problems on binary search. Thank you.